For the second part of the introduction to coordination compounds, I'm going to show you several examples of these metal complexes so that you can get used to what they look like and what to expect from these types of interactions. I'm going to start with coordination number 2 and work my way up to coordination number 6. You understand that we can have higher coordination numbers, but we are not going to go past 6 for this brief introduction. Coordination number 2, you have 2 ligands and a metal, is going to be rare. It's going to require those ligands to be rather large because most of the time the metal will need more electrons than 2 ligands can provide unless they're very late transition metals, like gold, for example. This happens to be still electron deficient. Just think about that nitrogen wants to have an octet rule, but gold does not, and that's obviously because gold is not a main group metal. Gold is a transition metal, which also has d orbitals, so we have those 10 electrons for those d orbitals that can be filled, as well as the s and the p's. So gold is really, and most of the transition metals are really after 18 electrons compared to 8 for the nonmetals, for the main group metals and nonmetals, okay, what we have been used to so far. So linear geometries are rare, as I said, and so you need to be able to determine the charge of the metal, so that we need that for naming, and it's just important. And so you might know that these are amide ligands, so that they have a -1 charge, but if you don't remember it, there's a method you can use to determine that. If you take a look at the electrons on nitrogen, there are 3 bonds shown, and that's just 6 electrons, and we know that's just not true. So we either have a lone pair, that's one option, and the geometry for that would be pyramidal. And if we had a pyramidal shape and we had an X-ray structure, we could get the angle sum here, right? So if each of these bonds is roughly 110, we should have an angle sum of about 330 degrees. If this was flat, so the other option here is that this nitrogen makes a double bond to gold. That is another option, and then the angle sum would be 360 degrees because it would be completely flat, and each of these angles would be 120. So the inorganic chemist usually doesn't distinguish or indicate that. That's for you to determine, or if there's X-ray data in the paper, then you have evidence for that. You might want to draw the double bond in or not, but usually that's just neglected, and you have to understand that. And so, but either way you draw it, if you detach the 2 electrons, since it's a donor bond, both electrons from this bond, I'm going to detach and put it back on the nitrogen. So I have the two bonds, which is 4 electrons, and now I'm putting the 2 electrons from the bond back on there. If I simply look at the formal charge of nitrogen now, which would be -1, that can help me determine the charge of the ligand. So both of those are amides, -1, -1, and if we have an overall plus charge, then that means we have gold 3. So this would be a gold 3 compound. Again, I just want to point out that coordination number 2 is fairly rare. Much more common is coordination number 4 and then 6, but I said we go in a row. So coordination number 3 would be trigonal planar. Could also be pyramidal, but it happens to be trigonal planar for the most part. Again, we have amides here, so the oxidation state of nickel here would be 2. This is a nickel 2 compound. If you look at the ground state electronic configuration of nickel, it's going to be 3d8 and then 4s2, and so nickel 2 would lose the 2 electrons, so we would have 8d electrons, and so sometimes we refer to this nickel complex as a nickel d8 complex, implying that it has a +2 charge, and that will become important in the next slide. But again, you should just know -1, -1, -1, and +2 leads to the overall charge, and we'll need that for naming, because we're going to name this yada 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 nickelate or nickel 2, and we'll get to that in the next lecture. For coordination number 4, which is actually not all that rare, the nickel D8 complexes display this square planar coordination number here, and if you have skinny linear-like ligands, and it will prefer to be square planar, and that is actually because the dz squared orbital here, which looks like that, is full. And so if you have electron density here above and below, it's going to force that into a square planar geometry. And only if you bulk up your ligands here, you can tell the triphenylphosphine here, so that's a neutral 2-electron donor. The chloros are -1, so again we have nickel 2 in both of these cases. And so a very bulky geometry can force this geometry into tetrahedral, but it will prefer to be square planar, as I've shown here. And so there are several different examples of D8 complexes that prefer that. So platinum 2 and palladium 2, platinum and palladium are right under nickel. Those D8 complexes are always square planar. They're never tetrahedral. So you can actually bulk that up as much as you want, and you're not going to force this into a tetrahedral geometry, which actually is used as a trick. You know, palladium compounds are and platinum compounds are highly active as catalysts, and so if you can create a steric strain by making these ligands bulky and still get them to coordinate to the transition metal, you've created reactivity. So there's a couple of ways to increase reactivity of a catalyst or a potential catalyst. That's by steric strain, messing with these comfortable 90-degree angles, and then also reducing electronics. So if you have something that's not 18 electrons, and so if you accomplish that, you have most likely a potential catalyst. Examples for square planar D8 complexes are also rhodium 1, iridium 1, and then gold 3, which we saw earlier, but of course not the tetrahedral geometry. So here's a crystal structure of an iridium 1 compound, which again, iridium 1 is D8, so we expect it to be square planar. And so there's already, we've seen the chloroligand, and so here's carbon dioxide. So that's pretty easy to understand that we have a lone pair of electrons on carbon monoxide. This ligand is called carbonyl, and this is just a neutral phosphine ligand. This is a monoanionic chloride ligand, so that's the one that's -1 charged. And so if iridium is indeed +1 in there, then this interesting ligand here, which seems to have a carbon with only 6 electrons, but again, I told you that that we don't really indicate that there could be a potential double bond. But this is going to be something very unusual. It's called a carbene, and we will have some slides on those. And we can indeed look at as carbene as 2-electron donors and 6-electron species, or we can also look at them, but there are different types of carbenes that have different they are distinguished depending on whether there's a double bond or not. For now, just focus on the geometry of this iridium. You can kind of see here the crystal structure nicely shows you that these are 90 degrees. So that's a nice example. There's a paper published by Kuchen back in the 90s. He actually tried to bulk up. He wanted to know the breaking point of when a nickel D2 converts from square planar to tetrahedral, and so he started bulking up these. So triphenylphosphine is going to make, if it's truly triphenylphosphine, it's going to make a tetrahedral geometry. And so then he just messed with the bulk of one of these groups, and so he put a benzyl group instead of one of the phenyl groups, and that was enough just to have this equilibrium between tetrahedral and square planar. And he was able to grow different crystals, one showing the square planar geometry, one showing the tetrahedral geometry from different solvents. So that's quite an interesting paper. Another interesting thing about nickel D8 complexes is that tetrahedral ones, they will have a bluish green color, and they will be paramagnetic, and square planar nickel D8 complexes are usually reddish orange, and they are diamagnetic, so you can take an NMR of those. So you can recognize, you might in the lab make a square planar and a tetrahedral complex. We used to do that, and it's kind of fun to do. Okay, so here's another example of a platinum D8 complex, right? So we know the amines are neutral. We know the chloros are monoanionic. So again, we have platinum 2+, which means we have D8 square planar geometry. In the case of platinum, it cannot go tetrahedral. This is actually the cis isomer here, right? So if you have something square planar, you can have cis and trans isomers. If it's tetrahedral, you do not. So the cis isomer actually is called cisplatin, and it's used as a cancer-fighting drug. Before I move on to coordination number 5, let's have a quick ligand review. Focus on those nitrogen-containing compounds. We either can have 2 electron neutral donors, so-called amines, where nitrogen has 3 attached alkyl groups or groups. Silicon is not an alkyl group, right? So it doesn't matter. But if you have 3 groups, so any primary, tertiary, or secondary amine is going to be a 2 electron donor. If you remove one of these groups and replace it with a lone pair, you end up with an amide. So those are the 2 electron or monoanionic ligands. And similar are the phosphines, arsines, and stibines. Of course, this is just group 15. We're replacing nitrogen with phosphorus and arsenic and antimony, so it's no surprise that those are neutral donors, and they have similar names: amines, phosphines, arsines, and then stibines. And they each have, of course, a lone pair of electrons on the group 15 element, so that makes them Lewis bases, and some of them are better than others. We have phosphines and amines that are very common. If you replace one of those groups, as I said, instead of R3, we have R2 now. It's going to be monoanionic. And if you remove one other group, we get an imide. So we have amines, amides, and then imides. That's just a name to distinguish them. And so this would be a dianionic 2 electron. We'll talk about the electron donors later when we discuss 18 electron rule. So you should be able to look at any ligand and determine the charge of it. Okay, and so this may be on a quiz. I may quiz you on that, so you should be ready on it about it, right? If you just know it, this is an amine 0. That's fine. You can fly through this. If you don't know what to do with it, you can figure it out by the method I've shown. So I encourage you to pause the video, go through it, and then I'll go through this rather quickly. So here we go. If we move on to this next one here, first thing you want to do is you want to fill up the octet. Any missing electrons are going to be attached to the element in question, which is oxygen here. And so you may recognize right off the bat it's an alkoxide, it's monoanionic, but if you don't, you detach the electrons from the metal, you put them on, and now we have a formal charge of -1 on this oxygen, just like an alkoxide would be a -1 charge. So we have determined that. This next one is an amide. We just had it on the other slide. Method is put the lone pair in there, cut it off, put it on, -1. And if we look at the one directly below it, it's the exact same thing, except we don't have a lone pair. We have the electrons on between the metal and the nitrogen. So if you remove all of those electrons, that's 4 of them, and put them on the nitrogen, you end up with also a -1 charge. So those are just different ways of showing the bonding. One has a double bond, one has not, but both of those ligands are monoanionic. If I remove one of these groups here, obviously I'm going to add electrons to it. So if I cut that off here, I have a nitrogen with an R group, and then all 6 electrons are put onto nitrogen, and that gives me a -2 charge. And so the structure right here is also -2, so the ligand here would have a -2 charge. And it doesn't matter if you have a triple bond or you don't show it. If you don't have a triple bond, you're missing electrons, and you add the 4, disconnect, and so this will look the exact same way. So we have a -1 charge. This one is just a bromo ligand, bromide, which is going to have a -1 charge. The oxygen here, it's like oxide, so we're missing 2, disconnect, so we end up with a -2 charge. So not an alkoxide, obviously. It's like an oxide, which oxygen you expect to be -1. The alkyl group here is -1 charged. If again, carbon has a valence of 4, and then a formal charge would be -1. So it's not very difficult to determine the charges of these ligands, so be ready to do this on an exam. Moving on to coordination number 5, we have 2 different possibilities for the geometry. Trigonal, I just realized I misspelled that. Trigonal bipyramidal and square pyramidal. And so there's a really low energy barrier between these 2 conformations. So this exchange of axial and equatorial ligands, right? Remember, we have axial positions here that are chemically equivalent, and then equatorial here. We discussed that earlier when we talked about Vesper theory. So if we took a carbon NMR, right, so these cyano groups each have carbon, you would expect 2 different singlets or signals for those 2 axial and equatorial ligands, but you don't see that because at room temperature there's an inter-exchange between the 2 positions. So and that the speed of that exchange is so fast that the NMR time scale cannot detect the difference, so it just shows up as a singlet. So there's another example where we can use IR to observe that as well, and that's when we are looking at these carbonyl ligands. Here we have the carbonyl ligand, which I mentioned once, but it's simply carbon monoxide, and it has an interesting characteristic, and that's because the negative charge is on carbon and not on oxygen, and we know that oxygen is more electronegative than carbon, so it should have that, but electronically it just can't, and then it does. It's a sigma donor, so it donates 2 electrons to the d orbital here in iron. And in IR, if you know that if we have a carbon triple bond, it's about 2100 per centimeters, but we can also observe different kinds of stretching frequencies that are closer to carbon oxygen double bonds. So there's something called pi back bonding, and that occurs when you have electron density in a metal, and it actually donates into the pi star. So that's an anti-bonding orbital from molecular orbital theory, which we'll revisit at some point and look into more detail. But if you have a transition metal that has electrons in an orbital that's not engaged in bonding, it can donate electron density into that pi star orbital, and it will push that triple bond back onto the oxygen, the electrons from that third bond, from that pi bond, and have more of a double bond character. And so if we look at frequencies of free carbonyl or carbon dioxide that's not bound, we have a frequency of 2143. And so here are different examples where pi back bonding increases as you go down. So the lower the stretching frequency, the higher the carbon oxygen double bond character. So here the 1750 for the titanium hexacarbonyl complex is much closer to what we would expect for like a ketone or something like that. So that's just something we will revisit. And as I said, there's a low energy barrier between the trigonal bipyramidal and square pyramidal geometry. And the person who studied that, his name is Barry, And so we call that the Berry pseudo rotation, where we have, once again, we have axial and equatorial positions, right? We do know we have vibration, and so all that needs to happen is for these two carbonyl groups to vibrate a little bit, and then if these are pointing down, then you are going to get an exchange. So I've got somewhat of a mechanism here. So you go from a trigonal bipyramid to, if these move all the way out, you go to a square pyramidal geometry here, right? And then the color coding here is black equatorial ligands, and then when the two axial ligands now switch, they turn into equatorial positions. So we have the axial position here turning into equatorial position. And so as long as that movement is faster than either the IR timescale or the NMR timescale, you cannot distinguish the difference between them. But we can do, we can cool this down, the instrumentation, and sometimes you can observe the different stretching frequencies. And so we'll look at dynamic NMR at some point. Coordination number 6, we already said we have, these are the Werner complexes from earlier here. We can have cis and trans isomers. We can also have facial and meridial. So if we have 3 of the same ligand, if they are all in one plane here, that's called meridial or mer. So we have fac and mer versus cis and trans. And then facial is if all 3 ligands are facing you. Facial, so if you were to build this is down the C3 axis that you should be familiar with from point group theory. And as always, you should be able to tell me what the oxidation state of cobalt is here in each of these compounds based on the ligands attached and the charge of the ligands and the overall charge of the metal. We can have chelating ligands. That just simply means that the 2 points of attachment are tethered. Ethylene diamine is a neutral ligand that is bidentate, right? Dentist, teeth. So you have 2 points of attachment, 2 teeth biting into your cobalt if you wish. And so you can have, we remember this from point group theory, we get these propeller-like geometries, and we can have a right-handed and a left-handed twist, and so we can have delta and lambda isomers. Sometimes if you take the 3 points that point towards you and you draw a triangle, and then you do the same with the triangle that's in the back. You know, this is kind of sloppy, but you can kind of see if it's right-handed or left-handed. So if this is in the front and this goes to the back here, front, back, then this would be, you would have to twist this clockwise in order to twist it into the board. Whereas if you do the same thing here, now we have a right-handed twist, so you would have to turn this counterclockwise to make this twist into the board. So that can help you visualize that. Of course, if I draw it in ChemDraw, it's much easier to see. And so although we don't really have Newman projections in inorganic chemistry, but you can kind of put this octahedron on a Newman projection, and you would have the same thing here, right? So this would be the delta isomer, and this would be the lambda isomer. Again, if you can see this is towards us here, and this is in the back of the board. So you can kind of see how this blade turns into the board or the plane of the paper. So that would be the delta, and whereas this one is up front, it goes this way here, where you'd have to twist it this way in order to make it in the board, and that would be the lambda isomer. Other examples of chelating ligands: oxalic acid. If you deprotonate that, it can be, so now it's dianionic. Of course, it will coordinate. Let's see here, right? I have a chromium complex that has the oxalate ligand. It's a great chelating ligand. And then this can also have lambda and delta isomers. So oxalate as a ligand, oxalato. We had ethylene diamine, and so a phosphine, a diphosphine, is also a good example. And if you think about it, right, we make with ethylene diamine and with diphenylphosphine. Here we always make a 5-membered ring, which are very, very stable. 6-membered and 5-membered rings are sterically not strained. In fact, the 5-membered ring is actually less strained than the 6-membered ring. And so we call this ligand here just DPPE for short, you know, instead of 1,2 bis diphenylphosphinoethane, right? We have ethane, we have a diphenylphosphine, we have 2 of them on the first carbon and the second carbon, so it's how you would name it for organic chemistry. If you have a carboxylic acid, like acetic acid here, this would be acetic acid. If you deprotonate you get a carboxylate. This would be kind of strained as a ligand, but it does. You can onto smaller metals like copper. You can have these chelating ligands that are carboxylates. Of course, this group, the R group here, is replaceable, so you can modify it somewhat. Here we can also use chelating ligands as bridges. This is also a carboxylate, but this time it's bridging, and so sometimes you can even get some metal-metal interactions. And so these bridging complexes, they get the symbol mu. In the next chapter, we will discuss naming in detail, and that mu will come back. Yeah, I know my mu's look like m's or something else, but this is a mu. Other chelating ligands, acetyl-ACAC, acetyl-acetonate, that's pentane-dione here, right? So we have 5. So this is called pentane-dione. If you deprotonate, actually the most acidic hydrogen is here. You get a negative charge. And so you'll have to know when you're looking at complexes like this that ligand is monoanionic. It has 2 points of attachments, so that you can determine the oxidation state of nickel, for example, right? So think about it, right? We have a minus and a minus, so this is also nickel 2. So is this square planar or tetrahedral? If all of these groups are pulled away from the center, it's not bulky enough to make it tetrahedral. So this is actually a square planar example. This can dimerize, or this is more than a dimer. It just coagulates to get its 18 electrons. It's still electron deficient, so it can do crazy things like this. You won't have to remember that, but you sure need to know what the ACAC ligand is, or the acetyl-acetonate. 2 points of attachment through oxygen to the metal, and these are chelating ligands. We saw very common bidentate ligands. We can also have 3. We can have tetradentate, pentadentate. Hexadentate will be the last one we are looking at. But so if you have 2 ethylene diamines tethered together, we call that diethylene diamine or diene ligand, and it has it's kind of restricted how it can bind, right? So it can either be facial or meridial. You can actually tether this some more and force it to be facial. That can be sometimes useful, like this pyridinophane. So we call this 2,1,1. I actually worked with this ligand at Indiana University as a postdoc. We made a bunch of palladium, platinum, rhodium, and iridium compounds in hopes that they would be catalytically active. It's called 2,1,1 because the bridges between these pyridine rings there's an ethyl and 2 methyl groups here, so 2 carbons, 1 carbon. There are others where you have 2,2,2, and so this happens to be the most interesting one because it can still attach to platinum, okay, but not with all 3. So it, you know, if you remember, platinum are square planar geometry preferred. In fact, we can have octahedral compounds with them, but the square planar ones are going to be, and cisplatin was one of those examples. Now ethylene diamine, no problem, but if you have 2,2,1, or then you have this third ligand that is leaning over and it's trying to, but it can't. So long story short, what that did, it created enough steric strain that it would actually fall apart in the solvent and attack the solvent. We used hexane as a solvent. It would do so-called CH bond activation. It's an oxidative addition of this carbon-hydrogen bond by this platinum catalyst, and that can be pretty important. Now, I wasn't the original thinker of this this stuff. I just came in as a postdoc and worked on that a little bit, and it was quite exciting to see these highly reactive catalysts. But so this is why you want to make ligands, so you can create a host, ligand host, that creates a steric and protective environment, right? So you need a reactive environment and then a protective environment, and if you can create steric strain, I mentioned that already. This ligand here, 1,4,7-tricyclononane, this has 2, 2, and 2. It also coordinates only on the facial side if we are talking about octahedrons. So that's just another example of a tridentate ligand that's tethered. The triazyl borate is another one of those that is confined to see, we have these 1, 2, 3 points of attachment. So for an octahedron, it has to go facial, shown here on the right. What you have to remember here, if I ask you to determine the charge of the metal, which we can't here because it's just M, so we don't know. We don't know what the other L's are here either. But remember my method of detaching the electrons. So if I detach the electrons, I end up with a formal charge of 0 on each of these nitrogens. However, because I have a negative charge on the boron, this is a monoanionic ligand. So you sometimes have to look at the entire ligand. Same is true for carbon monoxide, right? So carbon monoxide, if you detach that from the ligand and you only look at the formal charge of carbon, you might mistakenly assign a negative charge to carbon monoxide, but it's not, because there's a positive charge on oxygen. So the carbonyl ligands are neutral, despite the fact that it has a formal charge on carbon there. Okay, so same is true for boron. We have crown ethers. Those are good chelators. 18 crown 6, right? The 6 referring to the 6 oxygen, the 18 referring to the carbon. 2, 4, 6, 8, 10, 12. So 18 crown 6 simply means we have 6 oxygens, or 12 crown 4. This is just a more convenient way to name these. And then finally, oh, no, finally, not yet. We can have tetradentate ligands, so you just keep playing that game. You can tether 3 phosphine groups to a nitrogen, and so you can have all 4 points of attachments here. We call that a tripodal ligand, and so that can also be a very useful ligand because it can protect one side of your catalyst and then leave a reactive side open. Now we'll get to catalysis at some point. Finally, there's what I wanted to show you, the EDTA, which is a great, you might have used it for analytical chemistry for titrations. It nicely wraps around calcium and copper. You can titrate metals out of solution with it. It has 6 points of attachment, and so it's ethylene diamine, right, which we have here, and then tetraacetate. So these groups are acetate groups, so we have 4 acetate groups, and it completely encapsulates a metal and in 6 different positions. So that's your octahedral compound. Okay, so that's a lot of ligands, a lot of names, and so the book has table 7.1. I think the book I make a reference to has a different table, but it's in the coordination compound chapter. Here are all these ligands that we looked at that you might need to know. The amine, right? 2 M's, as I said. Ac here. Here are the crown ethers. Some simple ones like bromo. Carbonate can be a ligand. And so there's 3 slides worth of, here's your EDTA. We just looked at that. We looked at DPPE. And then we looked at oxalate. And so this is the end of the introduction to coordination compounds. The next section next week will be on how to name these, and then finally we're going to look at organometallic compounds.